Chapter 6 is on mechanical properties, and this lecture will cover elastic behavior, plastic behavior, stress and strain, and finally toughness and ductility. So to start off with the elastic deformation, I have the example of the human slingshot, and the quality of this video is pretty low, only 240p, but I like it because it's all shot from one camera. So here you have the victim. She's wearing a harness and she has bungee cords that are attached to these telephone poles on either side of her. And so when these guys on the quad apply a force to the bungee cords by pulling her to the right, these bungee cords are going to stretch. And when they stretch, they're going to, the more they stretch, the more they're going to try to pull back on the quad. And so let's see what happens.
1, 2, 3.
So as you can see, when they let her go, they pulled her back, applied more and more force, elongating these cords more and more. And then when they let her go, the cords tried to reattain their original length. So elastic materials, when you deform them, then let them go, they're going to try to reattain their original dimensions. So on the atomic level, for crystalline materials, this is how elastic deformation looks. You have your initial sample, you haven't applied any force. If you look at the crystal structure, you can see equal spacing in all directions. But when you apply a tensile force in this case, and you elongate it by some amount delta, you can see that these atoms are now separated by a greater distance. So these bonds are being stretched. And so these bonds are stretched, and if you remember from the bond energy versus separation of the atoms curve, when you stretch these bonds, they're going to try to pull back because the energy is increasing. And so when you release this force, the sample is going to retain its it's going to return to its original length. And you can see the crystal in the crystal structure, the atoms are arranged the same way as they were initially. And so elastic deformation is reversible deformation. And down here you have a force versus deformation curve. So for linear elastic deformation, when you apply a force, the deformation increases linearly. And then when you reduce that force, it also the deformation decreases linearly until when you're at zero force, you once again have zero deformation. Nonlinear elastic materials are not as common, but when you pull on them, they deform in a manner. They don't deform in a linear manner, but when you release the force, they still go back to their original dimensions. Plastic deformation, on the other hand, is permanent. It's not reversible. So if we take the same sample, here's its atoms, and we deform it beyond the limit of plastic deformation, then these bonds, say the bond of this atom with this atom here, it'll break. And so that bond breaks, whereas the bond between these two might not break, so then this atom will slide down to here, and that's called slip. So you can see this plane of atoms here, after the plastic deformation, slips down by one atomic separation. And same with these ones down here, they slip down. So now you can see from here to here, you've stretched these bonds, but you've also slipped a couple of the planes. And then when we release the force, because these planes have slipped, you have a permanent deformation. So you can see here there's no longer those stretched bonds, but because this plane has slipped, this sample is now longer than it was before it was plastically deformed. So you can see down here you have the linear elastic region. You increase force, the deformation increases linearly, and if you would have released it here, it had gone back to zero deformation. But if you go beyond the limit of that, then the material is no longer linear and it begins to plastically deform. You get slip in the crystal. And then when you release that, you still have these stretched bonds, so it still goes down this line here as if it was in a linear elastic region, but it doesn't go back to zero deformation because there's a permanent plastic deformation that occurs because of this slip. So when engineers talk about this, they use a quantity called stress. And in this case, tensile stress, given by sigma, is the force you apply in a perpendicular to the surface of the sample divided by the cross-sectional area of the sample. So you can see tensile stress is equal to tensile force divided by original cross-sectional area. And this original area is the area before any force is applied, because in most materials, when you apply a force, the cross-sectional area decreases. So you can see the units are pounds force per square inch or newtons per meter squared. And you'll notice that this is the same unit as pressure. So you'll often see stress given in pascals, which is a newton per meter squared. If you have a force that's not perpendicular to the surface, so this black arrow here, then you can split it into a tensile component and a shear component. So a shear force is when you take the surface that you're applying the force to and you push parallel to the surface rather than perpendicular to the surface, as with the tensile force. So shear stress, tau, is given by the shear force divided by that same initial cross-sectional area. So common stasis stress, if you've ever been skiing or snowboarding, then you've probably ridden on a ski lift. So the cables that a ski lift uses are in tension. So it's called simple tension, and the tensile stress in that case is just the force on the cables divided by the area of the cross-sectional area of the cables when there's no force being applied. Torsion, so this shaft here, this drive shaft, it's being twisted in order to move this cable. Torsion is similar to tensile stress, except instead of a pulling force, you have a torque on your sample. And so it's given by this equation, but you're not going to see this very often in this class. Another common stress state is compression. And so this rock formation, I believe it fell down a year or two ago, but it used to be in Arches National Park. So this rock up here is applying a compressional force to the rocks that are below it. And so it has the same form as tensional stress, but because positive force is defined as being that tension, because we're at compression, this force will be negative, so then this stress will have a negative sign as well. So both the columns and the arch in this bridge are in compression. So instead of talking about deformation, so we were talking about just delta before, which was the change in the length. When you're looking at materials from an engineering standpoint, you talk about engineering strain. So tensile strain, E or epsilon is given in the book, is equal to the amount of elongation, so delta, divided by the original length. So if this black box is the sample before it was before a force was applied, we have the original length, and then after the force applied, you can see that the length is now L0 plus delta. So the tensile strain is going to be that change in the length divided by the original length. And you can see this is in meters, this is also in meters, so strain, engineering strain, is going to not have any units. Shear strain is similar. If you have a shear force, so this red arrow applying a force to this top surface to the right, the shear strain is gamma is going to be the movement of that top surface, so delta x, divided by the original height of the sample, which is y, which will also be equal to the tangent of this angle. So if you're a mechanical engineer or a civil engineer, then you need to know the properties of the materials that you're going to be building with. So to measure those properties, people use a setup like this. You have these screws that pull this crosshead down, applying a force to a sample. And the sample usually looks like this. Say if you have a sample of steel and you want to figure out what its properties are, you'll cut it so that it has a smooth length that has the same area throughout. And then you'll have these bigger parts on the ends that aren't going to fail before this does. So all your failure will be in this middle region. And so you take this, you stick it in this machine, you pull on it. This device measures how much it elongates, and this load cell up here measures the force. So then you can find, from that you get stress versus strain, and you can go all the way until this material breaks. So in the linear region, so here we have stress, force divided by the unstressed area. Over here we have strain, which is the amount of elongation divided by the original length. In the linear elastic region, stress versus strain follows Hooke's law. So if you stress a material an amount sigma, then the strain is going to be sigma divided by the modulus of elasticity. So if you've taken physics recently, you might recognize this as Hooke's law for springs, where force is equal to the spring constant times the deformation. And this is where that comes from. And so this here, which is akin to the spring constant, is the modulus of elasticity, or it's Young's modulus of a material. So if you were to do this on a sample in the elastic region, when you're pulling on this, you're going to get a curve like this, and the slope of that curve is going to be your Young's modulus. Here is the value of Young's modulus for various materials. You can see ceramics, it's generally high, as with metals. Polymers, it's all very low. So that means polymers will stretch. You can stretch a polymer a long way and have very little force. So in the case of the human slingshot, they were able to pull the bungee cords very far. They were able to elongate them a whole lot, but it was only a little bit of force. And here you have composites. And you can see here the units are in pascals, which is the unit for pressure, as I said before, newtons per meter squared. And this is in gigapascals. So the stress versus strain, as I said, this is the linear elastic region. If you stress it, this amount, and then you release it, it'll go back to its original shape. So this is when you have a spring, you always want it to stay in this linear elastic region. If you push your spring too far, it's going to deform, and then when you release it, it's not going to take its original shape again. So if you look, if you go beyond the linear elastic region, though, you get into this plastic deformation region. You release it, you come back, and you have a permanent plastic strain. And like I said before, it's because of crystal planes slipping. So an important quantity to look at is the yield strength. So the yield strength is the stress, the tensile stress at which noticeable plastic deformation has occurred. So for metals, that's defined as a engineering strain of 0.002, or a percent elongation of 0.2%. So if you take a metal, you apply a tensile stress, and you get to this point so that when you release it, it's deformed by 0.2%, then that stress that you had it under was the yield strength. So here's a comparison of various yield strengths. Steel, as you can see, has a very high yield strength. You have titanium, tungsten, other metals. Ceramics, they don't have a high yield strength because they don't undergo plastic deformation. Because their crystals don't undergo slip as much because they have directional bonds. Instead of undergoing plastic deformation, they just crack and come apart. And same thing with composites and fibers. Polymers have a yield strength that's much smaller than most metals. And so again, stress strain testing, if we were to keep going until this sample breaks, we'll have a curve like this. Here you have the elastic region. So as you increase stress, you increase strain linearly, and then if you were to release it here, it would go back to its original dimensions. But if you keep going, you get plastic deformation. You start to get crystal slip of your sample. Originally, you're going to get to a point where you can't apply any more force. You can't apply any higher stress on your sample because it starts to fail. So right here at the tensile strength, which is the highest engineering stress that a sample can take before it starts necking. So if you get too much plastic deformation, you're going to get a region where the cross-sectional area drastically decreases, and it does it more so than other places. And if you keep pulling on it after that point, that neck is going to get narrower and narrower, and eventually it's going to break. So the tensile strength is the engineering stress immediately before it starts necking, and you can tell on this, and you can tell where it is by just going to the highest point on this stress strain curve, then reading off the engineering stress there. This point here is the fracture ultimate strength. That's the strength at which the material finally fractures. So here's a measure of different tensile strengths. So steel, once again, has a very high number. You have the other metals. Here you have composites, or not composites, but ceramics. Here you have your polymers. You notice they're significantly lower than the metals. And here you have your composites. And so if you're a civil engineer, you'll know that bridges are held up by columns. And if you were to make your column out of just concrete and there would be an earthquake, then there would be a much lower amount of force applied to this column until it breaks than if you were to have steel reinforcing in your column. So the reason why most concrete construction has steel reinforcement is because of this massive increase in yield strength you get from steel. So here's one kind of steel, here's another, here's a third. I'm not sure which they use, but if you were to have concrete by itself, you have a much smaller force before the concrete breaks and then it would crumble, whereas if you have steel in it, you still retain your structure even when the concrete has broken. So finally we have ductility. So if we have, this is our stress strain curve, we have our elastic region, we have our plastic region, and then we have failure. So ductility is the plastic tensile strain at failure. So this strain right here, if you go to your point of failure and you go down to the the value of the strain, this is going to be your ductility of this material. Whereas over here, so this material here would be perhaps a metal. So you have a very large ductility. It's going to stretch a long ways before it breaks. Whereas this blue curve is what it would look like for a ceramic. So you have a very high Young's modulus, but once you begin plastic deformation, you break almost immediately. So the ductility, which is once again the tensile strain at fracture, is going to be smaller than for metals. And so it's usually given as percent elongation. So you just take the engineering tensile strain at fracture and multiply it by 100%. So here you have, finally we have toughness, which is the energy to break a unit volume of material. So what that corresponds to is the area under this curve. So this green area here, if we add that all up, that would be the toughness of this metal. Whereas this blue area, including down here, would be the toughness of a ceramic. And this purple area would be the toughness of an unreinforced polymer. So as you can see, the one with the biggest area is the metal. So metals have a much higher toughness than ceramics and polymers. And so also you can see brittle fracture and ductile fracture. Brittle fracture occurs in ceramics or perhaps hardened metals when you have very little plastic deformation before your failure. That's a brittle fracture. So if you drop a glass cup, you'll have a brittle fracture. It's not going to bend very much before it breaks. And ductile fracture is when you have a lot of deformation, a lot of plastic deformation before your failure. So both metals and polymers undergo ductile fracture.